Let's take a look at a second example. This is the integral from negative infinity to infinity of 1 over 1 plus x squared. Now, graphically speaking, 1 over 1 plus x squared is a rational function that's pretty well behaved. It's never undefined. And it looks pretty much like a standard normal distribution bell curve. And here's negative infinity, and here's positive infinity. And we're talking about finding all the area A from negative infinity to infinity of that curve. So how do we deal with that? Well, as we stated before, the first thing that we're going to do is, since this is continuous for all values of x, we're going to break this up. And probably the nicest spot to break this up at is 0. So we're going to go from negative infinity to 0, or up to and including 0, I suppose, of 1 over 1 plus x squared dx, plus the integral from 0 to infinity of 1 over 1 plus x squared dx. Now, if you know that this is symmetric, and it is about the y-axis, you can still use things like twice the integral from 0 to infinity of 1 over 1 plus x squared dx. That's acceptable here. But you're not always going to know that those are symmetric, and they don't always have to be. So let's just go through it formally without using any of that symmetry. So we're going to break each one of these up. Let's call this a plus b and work on these separately, where a is the integral from negative infinity to 0 of 1 over 1 plus x squared dx. To deal with this formally, we have to introduce a limit. So we're going to do the limit as a approaches negative infinity of the integral from a to 0 of 1 over 1 plus x squared dx. There are a lot of different ways that you can integrate that, but the best way to integrate that is probably to just recognize it as being the derivative of the arctangent function. And we'll evaluate that between a and 0. And so this becomes the limit as a approaches negative infinity of the inverse tangent of 0 minus the inverse tangent of a. The inverse tangent of 0 turns out to be 0. So that's nice. And then we get the limit as a approaches negative infinity of negative inverse tangent of a, which we can write as negative the limit as a approaches negative infinity of the inverse tangent of a. Now, you're going to go one of two ways here with this limit. You're either going to start guessing and say, oh, well, it's going to negative infinity. Things get large when you go to negative infinity, or you're just going to make something up there. Or you're going to rely on the things that we learned in this class, because I had asked you at one point in this course to graph the arctangent, and you're supposed to know what it looks like, and that's going to help you evaluate limits. The arctangent function looks like this, and it's trapped between asymptotes that are horizontal at negative pi over 2 and pi over 2. And so as you tend towards negative infinity, the limit of the arctangent is pi over 2. So this is equal to the negative of negative pi over 2, which is pi over 2. For integral b, we have the integral from 0 to infinity of 1 over 1 plus x squared, which, by the way, is going to be terribly similar. And this is going to be the limit as b approaches infinity of the integral from 0 to b of 1. I don't know why I wrote it as a capital B there. B of 1 over 1 plus x squared dx, which is the limit as b approaches infinity of the arctangent of x evaluated between 0 and b, which is the limit as b approaches infinity of the arctangent of b minus the arctangent of 0. We saw in the previous example that the arctangent of 0 was 0, and as we head towards positive infinity, the limit is pi over 2. And so this is simply pi over 2 plus pi over 2, which is pi, which strangely enough means that all of this area underneath this curve is pi. That's weird, huh? But there it is. Pi over 2 plus pi over 2, which is a plus b, is pi. And so this converges. All right, let's take a look at one more type 1 improper integral for today. The integral from 1 to infinity of 1 over x dx. Does this converge or diverge? This one's also pretty straightforward in terms of its mechanics. This is equal to the limit as b approaches infinity of the integral from 1 to b of 1 over x dx, which is equal to the limit as b approaches infinity of the natural log of the absolute value of x evaluated from 1 to b, which is equal to the limit as a b approaches infinity of the natural log of b minus the natural log of 1, but the natural log of 1 is 0, and this is equal to the natural log of infinity. And hopefully, again, you know what these curves look like and how they behave. And as x goes to positive infinity, this curve goes up to positive infinity. And this does not exist. And so the integral from 1 to infinity of 1 over x dx diverges. Fantastic.